if we divide a positive integer n by another positive integer lowercase d, then what you obtain is this. This is what I teach my college algebra students about taking what might be an improper fraction and rewriting it as an integer plus a proper fraction. And this is sometimes called the division algorithm. But if you take this equation and then you multiply both sides by your denominator d, then on the left side you end up with n, and on the right side you end up with qd plus r, where r is your remainder. If you take the original numerator and your remainder to be congruent, this is what we call modular arithmetic. And in this case, since we're dividing by the number d, this would be arithmetic modulo d. So modular arithmetic works just the same as our typical arithmetic, adding and subtracting and multiplying and dividing, except that on every opportunity, we reduce all of the numbers, every term in our arithmetic, every factor in our arithmetic, down to the least positive integer in its congruence class. And what I mean by congruence class is this. If I'm dealing with modulo 5, for example, then 2 is the same thing as 7, which is the same thing as 12, which is the same thing as 17, which is the same thing as 22, which is the same thing as 27, and so on. So a congruence class represents a set of like infinitely many numbers that are all 5 apart from each other in this case, because we're doing arithmetic modulo 5. So if I had 17 modulo 6, or 17 mod 6, what is the least positive integer congruent to 17 mod 6? Five. Five is also congruent to 11 and 17 and 23 and 29 and 35 and 41 and 47 and so on and so on. So right, there's infinitely many numbers in this equivalence class. So if I had then something like 40 plus 52, what I could do is I could add 40 plus 52 is 92, and then think, what is 92 modulo 3? 2. But a separate way that's just, considered to be slightly more efficient in a lot of cases is before I do the arithmetic, before I do the adding, I could go ahead and do mod 3 to each of these numbers, where 40 mod 3 would be 1, 52 mod 3 would be 1, and then of course 1 plus 1 is equivalent to 2 mod 3. And you see, it doesn't matter the order in which we do things. It doesn't matter if I take the mod first or if I take the mod after. Modular arithmetic is flexible in that way. You can decide when to take the modulus. Okay, if I said 3 times x is congruent. 3 times x is congruent to 1 mod 11, then what is x? And don't tell me 1/3. These are supposed to be positive integers, okay? Yeah, it's 4. Good job. How did you figure that out?
Well, we have the 1 and then mod 11, so the multiples of that, or the congruence class would be 1 and then 12, and then 23, but you take 12 equals 3x.
Yeah. Very good. So yeah, 1 plus 11 is 12, and then you divide by 3. Perfect. You pointed out the other numbers in the congruence class would be 23, but that's not divisible by 3. And then what? 34, which is not divisible by 3, and then 45. 45 is divisible by 3. That would be 15. And then 15 mod 11 is, oh, it's 4. So really, the only possible x is 4 in this case. Is this easy or is this hard, Hudson?
I'm still deciding.
Okay. There's some big sighs coming from that part of the classroom. What is 4 raised to the power 4 congruent to mod 7? What's the least positive integer congruent to 4 to the power 4? And by the way, don't use a calculator when you answer these questions. If you have to use a calculator, then you're probably doing it wrong. Okay? Like, the wrong way to do it would be to say 4 to the power 4 is 64 squared, and then sit down and figure out 64 squared, and then subtract 7 away from that number, 64 squared, until you get down to a number less than 7. It's a way you could do it, but that would definitely be the hard way. But you shouldn't have to use a calculator for these problems. Instead, I would think of 4 to the power 4 as being 4 times 4 times 4 times 4, right?
You take the mod of each of those.
Which is, again, I only care about what's congruent. So this is 16 times 4 times 4. But what's 16 mod 7? 2. And 2 times 4 is 8. But what's 8 mod 7? 1. So again, if I only care about what this is congruent to, then x is congruent to 4. 4 to the power 4 is congruent to 4 mod 7. You see how that's way easier than figuring out what 4 to the power 4 is? Yeah. Okay, if the time is currently 8 a.m., what time will it be in 50 hours? Because this is basically the question, 8 plus 50 is congruent to what mod 24? And you say, well, 50 mod 24 is 2. And so we're talking about the number 10, 10 a.m. this is a real tricky one. Well, maybe not the last. Let's do the last one first, and we'll come back to that tricky one. The last one says, if today is Tuesday, what day of the week will it be in 100 days? Sorry, 1,000 days. What day of the week will it be in 1,000 days? I'm putting my money on, well, I'm not going to say it. Monday. So Tuesday is the number 2 because it sounds like Tuesday. And then we're going to add to it 1,000 days and figure out what that's congruent to mod 7, because there's 7 days in a week. And so everybody knows that 1001 is a multiple of 7. And so this is like -1, right? Because it's 1 less than 1001. So 1000 is congruent to -1, mod 7. And then 2 plus -1 is 1, and 1 is obviously Monday. Because it's 1 less than Tuesday.
That's where I was like, it doesn't matter. Start. Yeah, it does.
Sunday is the week end, not the week beginning.
Well, no, because if you start on Sunday, Sunday would be 1, Tuesday would be 3, not 2.
Yeah, but you'll
So
still
it does matter which way you start on.
You'll get Mondays, the right answer still.
Yeah, because it's still -1.
Yeah, you can number the days any day you
I
what you
know
want. Yeah.
the numbers, like you'll say 3 instead of.
Isn't it just because Monday is one before Tuesday? Not that it starts on Monday?
You're right.
Yes.
Yeah, it doesn't matter.
The only thing
It doesn't matter which way you number the days of the week. Their relative position to each other matters. Yeah.
Obviously. I listen. Of course.
Yeah, so mod 7 is difficult. What was actually going through my head is like, okay, 700 is a multiple of 7. 350 is a multiple of 7. That puts me at 1050. And if I subtract 49, which is a multiple of 7, I get to 1001. And this is 1 less than 1001, so it should be -1 in the congruence class.
Can you just do the thing where you break up the 1,000 into like 10 times 10 times 10, and then do mod 7 to each of those? So it becomes 3 times 3 times 3, and then mod 7 to that, which would become.
You could. There's lots of ways to do this. Lots and lots and lots of ways to kill one bird with 2 stones. So the last problem that I have on screen right now is, like I said, a little tricky. What's 100 times 101 times 102 congruent to mod 103? Can anybody tell me how to do this without a calculator?
I have an idea.
What's your idea?
So if you subtract 103 from each of those numbers to get your mod, then you get -3 times -2 times -1. And then, so that's -6. And then to get the mod of 103, you just add 103. So that was 97.
Nice. So yeah, this product is congruent to 97 mod 103. Very good. And just to check, you could use a calculator, to check your work. Let's see what the calculator has to say when we weigh in on the calculator. We would say, I want 100 times 101 times 102, which is a big number. And then we want to take that and divide it by 103. And then what I want to do is I want to take this number and subtract away the integer part of it so that I get just the remainder, and then take that and multiply it by 103 so I can get back, the whole number part of the fraction and remainder. And it's 97. So it works. Any questions from anybody? No. There's, by the way, there used to be I can't remember who it was anymore. I know I've seen this somewhere, but I just don't remember if I saw it online or if this was a friend who used to be able to do this. So I've seen this party trick before. The way it works is you walk in, to the room and you say, Matt, what's your birthday?
June 14th.
It's a Tuesday. And then Hudson, what's your birthday?
June 30th.
You're born on a Saturday, right? But you have to tell me the year, right? Like you have to say, so you have to say like June 30th of like 2005, and then you say that's a Saturday, and you tell them immediately what their day of the week birthday is. The way that party trick works, the way people are able to do this, is you memorize not every single day of the week for every calendar day for the last 100 years. But what you do is you remember like certain anchor days. Like maybe you remember what day of the week was it on January 1st of the year 2000. And then you remember what day of the week was it on January 1st of 1990. What day of the week was it on January 1st of 2010? And if you know your audience, like if I know my audience is all 20-year-olds, then I only have to remember January 1st of 2000. Okay, so what about after that? You remember certain numbers associated with every month. Like in the month of January, the number would be 3. Because 31 days in January, mod 7 is 3. For the month of February, the number is 0, because 28 mod 7 is 0. For the month of March, March has how many days? 31? So it would be 3 from March plus 3 from January is 6. And actually, I'm getting ahead of myself, because if you were thinking about March, really the number is 3, but April would have the number 6, because you have to take into account the 3 from January and the 3 from March. So if you get a date in April, you've got to add 6 to it. And then you have to remember how many each year is worth. And I think the number 364 is a multiple of 7. So every year is just worth 1. And then on leap years, where you get an extra day, a leap year is worth 2. So you got to remember where the leap years fall. And then In theory, someone should be able to tell you your birthday, and then using modular arithmetic and counting up these point values for certain years and certain leap years and certain months, and then the day of the month, right? So if you tell me your birthday's on the 30th, that's 2 mod 7, then you can quickly assign numbers or days of the week to people's birthdays. And so I've never bothered practicing this myself, but I've like seen other people do it, and it's genuinely cool if you're quick at it, even if you know what the trick is. But yeah, if you really want to impress somebody. If you wanted to sound really, really smart, and you are like going on like a first date with somebody you met on Hinge, right? Think, how old is she? She's probably about, I don't know, 22 years old, and then you memorize what January 1st of that year is, and then that way when she tells you her birthday, be like, oh yeah, that was a Wednesday. And she's like, what? You say, yeah, I'm a savant. I'm like Rain Man.
Oh my gosh.
You guys know Rain Man? Too old for you guys? There's this movie called Rain Man. And I won't spoil it for you because I know you want to watch this 1988 drama.
Sure.
But this character is like a very, very gifted autistic man who can like do all sorts of counting and math problems in his head. And so, anyways, if you hear someone reference Rain Man, that's who they're talking about. Okay, moving on. Consider the set of numbers 0, 1, 2, 3, 4, 5. When we bestow a binary operation on this set of numbers, like addition modulo 6, then it becomes a group. When I say binary operation, what we mean is a rule that combines two elements to form another element. Examples include addition, multiplication, and composition. A group is a set of elements with an operation that meets the following requirements. So not every binary operation is going to work, but in the case of this set of numbers, addition modulo 6 does work. The requirements for this to be a group is closure. In other words, I can't get a number by doing addition modulo 6 that puts me outside of this group. Division would be a binary operation that doesn't work, because I could say 3 divided by 2, and that would give me 1.5, and that element doesn't belong to the set. So this would not be closed under division. And it wouldn't be closed under just plain old addition either, because 3 plus 4 is 7. But it is closed under addition modulo 6. So we have closure. Associativity means that the binary operation we're using has the associative property. You know what that is? Identity means that my set has an element that behaves like the number 0 does under addition. In other words, an element plus 0 gives you back the same element. It's the identity element. And then inverses means every element has a buddy, and when you combine an element with its inverse using your binary operation, it brings you back to the identity. So like 4 is the inverse of 2 under addition mod 6, because 2 plus 4 is equivalent or 0 in this group, right? 2 plus 4 is congruent to 0. So a group is a set of elements with an operation, and it has to meet these 4 requirements. If you fail to meet any of these 4 requirements, we don't call it a group, we just call it a set with an operation. So group has a fancy meaning in mathematics. Is the following a group? The set is 0, 1, 2, 3 with addition modulo 4. When you get a question like this, you have to come up with your checklist. Does it have closure? Does it have associativity? does it have identity? Does it have an identity element? And does every single element have an inverse that brings it back to the identity? Okay, one at a time. Does this have closure? Yes. Does it have associativity? Yes. Does it have an identity element? Yeah. 0 is the additive identity, so anytime I'm adding, 0 will be the identity. Does every element in this set have an inverse? Zero and 0, so 0 is self-inverse. 1 plus 3, and then 2 plus 2. So, sorry, I should have made that more clear. When I say every element has a buddy, it's also allowed to have self-inverses. I should say this can be itself. Like 3 plus 3 is equal to 0 mod 6. Cool. Is this a group? Does it have closure?
Yes.
What about 2 plus 3 mod 5? Two plus 3 mod 5 is 0, and there's not a 0 in this group. So there's also not an identity element. So this is not a group because we need 0. Okay. Moving on, is this one a group? I've got a 0. Does it have closure?
I think so.
What about 2 plus 3? What's 2 plus 3 mod 6?
-1.
Oh, it's 5.
So,
Or 11.
so it does not.
5. I'm missing a 5, right? I need to have a 5. And if I don't have a 5, I don't have closure. Because of the 2 plus 3 problem. Okay. It turns out that every finite set of non-negative consecutive integers starting with 0, like, for example, 0, 1, 2, 3, 4, 5, is a group when paired with addition modulo n plus 1. We are not going to prove this. If you were to take a class in abstract algebra, that's kind of the branch of mathematics that would handle questions like this. There's a lot more to say about groups, by the way. There's groups that are commutative, like the ones we're talking about, because addition is a commutative operation. There's groups that are not commutative. There's other ways of defining groups that reflect more of like geometry than arithmetic, like the groups of the different ways you can rotate objects or reflect objects or rotate and reflect objects. Those all represent groups. And so it's a neat class, but we're not going to go over everything from abstract algebra. I'm just cherry picking a few ideas that might help with number theory. Is the following a group? It's the set 1, 2, 3, 4 with multiplication. mod 5. So now forget about addition, because now our binary operation is multiplication mod 5. We got to go back to our checklist. Does this have closure? Matt thinks so. Connor, do you think so?
No.
No? If it doesn't have closure, then what two numbers would I multiply with each other mod 5 that would not end up in the set 1, 2, 3, 4?
Just kidding.
Yeah, so if you're checking closure, you've got to multiply 1 times 2, 1 times 3, 1 times 4. Those are all still in the set. 2 times 3 is congruent to 1 mod 5. 2 times 4 is congruent to 3 mod 5. And 3 times 4 is congruent to 2 mod 5. So yeah, we actually have closure. Do we have associativity? And yeah, we're not going to bother checking it for every possibility, but multiplication has the associativity property, and we're assuming that it continues with mod. We'll just move past that and skip to identity. Do we have an identity element?
No, yes, because it's multiplication. It's the identity element.
1 is the multiplicative identity. 0 was our additive identity because 2 plus 0 equals 2. But this time, since my operation is multiplication, we have 3 times 1 equals 3. That makes 1 the identity, and we're good there. The last thing I have to check to make sure this is a group is inverses. We need to make sure that every element in the set can be multiplied by either itself or another element to give you 1, because now 1 is my identity, not 0. So 1 times what is congruent to 1? 1. 2 times what is congruent to 1? 3. 3 times what is congruent to 1?
2.
And 4 times what is congruent to 1? 4. So we have inverses. 1 and 4 are self-inverse. 2 and 3 is a pair of inverses. Is the following a group? 0, 1, 2, 3, 4 with multiplication modulo 5. Does it have closure? Yes. It has associativity. Don't worry about that. Does it have identity? Yes, it's the number 1. Does it have inverses? Does every element in the set have another element where I can multiply it mod 5 and get back to the number 1?
I don't think so.
We would have to ask ourselves the question, 0 times what is congruent to 1? And so there is no inverse for 0. So we fail the inverse question, and this is not a group. We can have a group if we get rid of the 0, but not with the 0. Is this a group? 1, 2, 3, 4, 5, 6 with multiplication mod 6. We got to check. Do we have closure? Why not?
Because 2 times 3 is 6, which would get congruent to 0.
Ah, you're right. And in fact, it doesn't even really help me if I add the 0 back in, right? Because then we wouldn't have inverses. We wouldn't have a way to multiply 0 times something, give me 1. And so this set is doomed from the start. Can't have closure, and you can't add any elements to give you closure. So consider the following set with binary operation, multiplication modulo 9. This is not a group, by the way. I won't make you guess. The first question says, do any of these elements have a multiplicative inverse? Well, for one thing, 1 times 1 is congruent to 1. That's good. What about 2? Is 2 times something congruent to 1? 2 times 5. What about 3? Is 3 times something congruent to 1?
7.
3 times 7 is 21. 21 mod 9 is 3. That doesn't work. Nope. So 3 does not, which is why this is not a group. What about the number 4? Four times 8 is 32. 32 mod 9 is 5. 4 times 7 is 28. 28 mod 9 is 1. What about, well, we got 5. 5 times 2. What about 6? 6 times something congruent to 1? Nope, doesn't work with 6. And what about 8? Is there 8 times something congruent to 1?
Yep.
Nice, that was fast. Cool. So we don't have 3 and 6. But we do have 1, 2, 4, 5, 7, and 8. These all have inverses. And so some of these have inverses, and that should say congruent to. What is different between the numbers that have inverses and the numbers that don't have inverses?
Well, with the ones that don't have inverses, like they're like factors of 9.
Yep.
Like,
Yep. So 3 is a factor of 9. 6 isn't a factor of 9, but
It's a factor of 18.
6 is still a number that's a multiple of 3, the way that 9 is a multiple of 3. 9 is 3 times 3, 6 is just 2 times 3. So here's what I want you to remember. Numbers in the set that do have inverses are co-prime to 9. And 9 matters because this is mod 9. The numbers that don't have inverses are not co-prime to 9. So numbers that don't have inverses are in a situation where the greatest common divisor between your number and 9 is greater than 1, right? That means it's not co-prime. So let's see what this says. Prove that if a number d divides both positive integers a and b, then d also divides a minus b when a is greater than b. So suppose d divides a and d divides b. Then there exists positive integers. We got to come up with a name for them. Let's call them m and n, such that a is equal to m times d and b is equal to n times d. That's just the definition of divides, right? So whenever I have a minus b, this would be the same thing as md minus nd. And since we have the distributive property, we can factor out the d and get d times m minus n. And since m and n are positive integers, m minus n is an integer. A is greater than b, right? So that a minus b is positive. We're assuming d is positive, right? So m minus n has to be positive. And then what we're trying to prove is that does d divide a minus b? And I think the answer is yes, because a minus b is equal to d times a positive integer. And so we can conclude that d divides a minus b. That's something I might write if I saw that on a test. Do you guys have any questions about that? Okay. Prove that a positive integer a cannot have a multiplicative inverse, mod n, if the greatest common divisor of a and n is greater than 1. So I think we have to ask, suppose A does have an inverse. Let's call it B. What it would look like if A has an inverse is that A times B is congruent to 1 mod n. And this implies that A times B is equal to some integer times n plus 1. Because what the modulus is doing is it's saying we're subtracting some positive integer multiple of n, or subtracting some integer multiple of n, right? So that we can get it reduced to the least positive integer. And so if I add some multiple of n here, now this is no longer just a congruence, but this is really equality. A times B is equal to D times n plus 1. But if the greatest common divisor between A and n is greater than 1, then there exists some I got to come up with a letter for it. Some number k such that k divides A and k divides n. And we're trying to find a contradiction. Because we're starting off this proof by saying, suppose A does have an inverse. But what we're actually trying to prove is that A cannot have an inverse. And I think the problem is that if I take this equation here and I subtract dn from both sides, AB minus dn is evenly divisible by k. Because A is divisible by k, n is divisible by k, and A minus n would also have to be divisible by k. There's also maybe a place where you have to rely on Euclid's limit here. Well, I guess the converse of Euclid's limit, so maybe not. But, right, there's factors in here. There's a k in here in both of these terms, and if I subtract them, it still doesn't get rid of the idea that this is divisible by k. So that means on the right side of the equation, 1 would have to be divisible by k, because this is no longer just congruence, but this is an equal sign. And so 1 is obviously not divisible by k. So we found a contradiction.
Wait, why were we looking for a contradiction?
Oops. So what we're trying to prove is that a positive integer a cannot have a multiplicative inverse mod n if a and n are not coprime. So what we did is we said, let's start by supposing the opposite. Suppose a does have a multiplicative inverse mod n. And if I start by supposing the opposite, that means we're going for a proof by contradiction. Suppose the opposite and then show that it has to be logically false. Okay, does that make sense? And so this is the full circle moment where I said, before we saw an example where the greatest common divisor between 3 and 9 would have been 3. The greatest common divisor between 6 and 9 was 3. And so there was no way that those could have a multiplicative inverse. But all of these other numbers, like 1, 2, 4, 5, 7, and 8, those are all co-prime to 9. And so they're allowed to have inverses. The other proof, where we say, how do you prove that those numbers will have an inverse? Not they're just allowed to, but they must have an inverse. That's a little bit more time than I want to spend in class on this, right? I'm not going to hit every topic in abstract algebra. I'm just going to hit the highlights. So it turns out, and this is another thing that we're not going to prove in class, but it turns out that every finite set of positive consecutive integers starting with 1, like 1, 2, 3, 4, 5, 6, is a group whenever you pair it with the binary operation multiplication modulo p, like multiplication modulo 7, as long as p is prime. And why would that work? Is because if p is a prime number, then all of those other numbers are co-prime to a prime number. And so every one of those numbers is allowed to have an inverse. I can't, prove to you that they must have an inverse, but we can now say that they're allowed to at least. I'll hit you with one more definition, and I don't want you to stress out about this if you don't understand it, because I'm not going to ask you any questions about this, but I at least want to say this during class. There's a term called a field in mathematics. If you've got a set of non-negative integers, so we're starting off with 0, and then 1, and then 2, 3, 4, 5, 6. When we give this set two binary operations, like addition and multiplication, we sometimes get a field, especially if p is prime and we're using addition and multiplication modulo p. A field is a set, and it's got two operations, and these are the requirements. It has to be a commutative group under addition. In this case, addition modulo p. And commutative just means that in addition to the other four requirements of being a group, your operation has to be having the commutative property, which is not true for all groups. It also has to be a commutative group under multiplication modulo p. Multiplication has the commutative property, but there are groups that don't, right? When you consider this, you are allowed to exclude the identity element of your first binary operation. When you think about whether your second binary operation is a group, you can ignore the 0, because the 0 makes it so we can't have inverses, right? But just pretend we don't have a 0. Do the rest of the elements form a group under multiplication? And then if those two things are true, the last thing you need is distributivity, which only applies if you've got two operations like multiplication and addition. But what I think is cool is that, like, the rational numbers are a field, the real numbers are a field, the complex numbers are a field, but those are all infinite fields that have infinitely many elements. But we can actually create finite fields. I don't know if anybody else thinks this is cool, but like I was talking about 0, 1, 2, 3, 4, 5, 6. This is a field with addition mod 7 and multiplication mod 7. All of those elements have both a additive inverse and a multiplicative inverse. Like 4 plus 3 is 0 mod 7, but also if I want to get back to 1 by multiplying 3 times something mod 7, I could say, well, 3 times 5 is 1 mod 7. So 5 is the multiplicative inverse of 3, 4 is the additive inverse of 3. And that's true for all of those elements. It almost seems like just a coincidence that that works, but I think it's nice. So we've got 9 minutes left in class. I want to quickly, man, I can't believe I ran out of time for 2 lectures. Let's jump to what I think are the cool parts. Euclid's theorem. Euclid was an old mathematician. We're talking about ancient Greece, like BC 300 or something like that. Euclid wrote a book called The Elements, and you can still read The Elements today and pick up a copy of it and see what Euclid wrote in there. But Euclid came up with this proof that there are infinitely many prime numbers. The other possibility, is that maybe there are only a finite number of prime numbers. Maybe there's only 2 million prime numbers, and then after number 2 million, it just stops, and every number after that is just a composite integer. But we find out there's actually infinitely many primes. The proof is a proof by contradiction, so we suppose the opposite. Suppose there are only n prime numbers. Multiply all of them together. And so we multiply P1 times P2 times P3 times P4 and so on. All the primes get multiplied together up to Pn. There's only finitely many primes, so this is a product of a finite number of factors. And P1 is like 2, and P2 is the number 3, and P3 is the number 5, and P4 is the number 7, all the way up to some really big prime, the last prime. Then we are going to add plus 1 at the end. And this is my number x. It's a really big integer because it's a product of all of the prime numbers plus 1. Notice x is not divisible by any prime number. It's not divisible by 2 because that big long product is divisible by 2, and this is 1 more than 2, so it must be an odd number. It's not divisible by 3 because that big product is divisible by 3, and then we move it plus 1, makes it 1 mod 3. It's not divisible by 5 because the big product is divisible by 5. When we add 1, this makes it 1 mod 5. It's not divisible by any of those primes. Well, if it's not divisible by any prime number, it can't be divisible by any composite number, right? Then it would have to be divisible by multiple primes. Anyways, it's not divisible by any number except for 1 and itself. So x is prime. And x is greater than the largest prime number, isn't it? So this is our contradiction, that we just found a prime number larger than the largest prime number. That means there cannot be a finite number of prime numbers. I like that proof because it's, I think it's easy to remember. You multiply all the primes, add 1. And it says something that's at least a little bit important. And I think today you've probably heard your entire life that there's infinitely many prime numbers. So this like result isn't a surprise to anybody, but try to imagine yourself living in like Greece, BC 300, you know, and you don't know the answer to this question. You don't really know if there's infinitely many prime numbers or if there's only 200 of them, and then maybe it stops. And so that might be a surprising result to an ancient Greek. We're also talking about Euclid's algorithm, and so Euclid's algorithm is also kind of attributed to Euclid, and maybe he came up with it independently, but I think this was also independently developed by all sorts of ancient civilizations, not just ancient Greece, but also ancient China, ancient India, ancient Mayans or Aztecs or whatever. A lot of people came up with this. The way it works is you take the largest number of the greatest common divisor here. In this case, the largest number would be 7,469. And then you subtract the smaller number. So like, what's 7,469 minus 2,464? 5,005. And these are the same. The greatest common divisor doesn't change when you subtract the smaller number from the larger number. And I might not have enough time to work out this entire problem, but this is based on the idea that, let me find it for you. The greatest common divisor is a number that divides both A and B. And that means it also divides A minus B. Okay? So if I have a greatest common divisor that divides 7,469 and divides 2,464, it will also continue to divide even when I subtract. And of course, I would take 5,005 and subtract 2,464 again and get 2,541, and that's still the largest number, so I'd subtract 2,464 again, and I would get 77. Now 2,464 is the larger number. So I'm going to subtract 77 and subtract 77 and subtract 77 and maybe even subtract 770, right? Because this is a pretty big number.
So it's just going to go into 630?
77. Is 630 a multiple of 77? Oh, the whole thing was a multiple of 77, wasn't it? So then you eventually get to a point where you get the same number twice, and that's actually the answer. So if you want to find greatest common divisors, that's actually faster than the prime factorization method in my mind, especially if you have a calculator in front of you. So instead of finding the prime factors and then selecting the least multiple of every prime factor and then multiplying it back together, you could just subtract the smaller one from the larger one over and over and over and over and over again until you see something like that happen.